Delaware Tech, Chemistry 100 and Chemistry 110 with Dr. Marc Taylor, Unit 5, Chemical Quantities and Reactions, and this corresponds to a title of the same name, Chapter 7 in your Timberlake textbook. So in this chapter, we're going to cover the definition of a mole, and the mole is just a very large number, and it's shown over here on the right side of the slide. 6.022 times 10 to the 23 is a close enough approximation. The exact number is shown in blue just below it. Then we're going to talk about the concept of atomic mass and molar mass and how they're related. We've already talked about atomic mass. We're going to talk about how that connects to molar mass. Then we'll talk about how to write chemical equations and the symbols used. We'll talk about how to balance equations. That's the concept of making sure that there are exactly the same number of atoms on the left side of the equation as there are on the right side of the equation. We'll talk about the 6 main reaction types. Then we're going to focus on one of those types, and in order to do that, we're going to look at a concept called oxidation state, also known as valence number. An oxidation state you've already been exposed to in some respect. In the case of ionic compounds, oxidation state just means the charge of the atoms. If you're in Chem 110, we'll talk about stoichiometry. Otherwise, we'll skip this for Chem 100. And then we'll discuss how energy is involved in chemical reactions. We'll talk about how energy is involved in the speed of a chemical reaction, known as reaction kinetics. And we'll talk a little bit about molecules called catalysts, which speed up the chemical reactions. We'll also talk about the heat energy that is either absorbed or produced in almost every chemical reaction, and that heat is referred to as enthalpy. So let's talk a little bit about some of the definitions. The mole. As I already mentioned, the mole is a very large number. 602 sextillion, 214 quintillion, 76 quadrillion exactly. It used to be an approximation, but in May of 2019, this was made an exact value. We estimate this number as 6.022 times 10 to the 23. That's close enough for our purposes. The molar mass is the mass of 1 mole of any substance. In other words, if you have that large number right above of that many atoms or that many molecules or that many formula units in the case of ionic compounds, it has a certain mass, and that mass will be different for every single different substance, and that mass is called the molar mass. So molar mass is the grams per mole of that material, or the grams per this many particles shown in the large number above. Then we'll talk about some of the reaction types. One of the reaction types is called combination, also known as synthesis, and this is where multiple reactants, typically 2, maybe 3, combine together to form a single product. The opposite of that would be to start with a single reactant, and this would break down into multiple products. This is known as decomposition. We also have 2 types of what are called replacement reactions, single replacement and double replacement, also known as single displacement and double displacement, respectively. Single replacement is where an element and a compound react to form a new compound and a new element, and a double replacement reaction is where 2 different compounds, usually ionic compounds, essentially swap cation and anion pairs to form 2 new compounds. We'll talk about the 5th reaction in the collection of 6, combustion reactions. And while combustion can mean a lot of different types of reactions, we're going to limit our definition to combustion to being only carbon-based compounds reacting with oxygen gas to form carbon dioxide and water, and that's the only way we're going to define it for these 2 courses. And then the 6th reaction is called oxidation reduction. We shorten that. The abbreviation that most people in chemistry use is redox. Instead of saying red and ox for reduction and oxidation, we just pronounce the word redox. And this is where one of the reactants loses electrons. That process is called oxidation, and one of the reactants gains electrons. That process is called reduction, and you end up making at least two new products in the process. Stoichiometry is the relationship of the amounts of different substances involved in a reaction. For example, if I know that 6 grams of one reactant will react with 10 grams of another reactant, knowing about the chemical reaction, I can predict exactly how many grams of each of the products that I will form, and these calculations are known as stoichiometry. We'll only be doing these in Chemistry 110 and not in Chemistry 100. Limiting reaction is something that comes out of stoichiometry. If you have two reactants, one of them is going to run out first. Unless you've absolutely calculated the exact amounts to react with each other, typically whenever you mix two compounds, one will run out first. The one that runs out first limits how much product you can form and is called the limiting reactant. The other one is referred to as the excess reactant. A catalyst is a substance that increases the rate of reaction without being consumed by the reaction. In other words, it can be used over and over and over again to speed up another of the same chemical reaction, one after the other. So you only need a little bit of catalyst to be added to a chemical reaction to speed up the rate of all of the molecules involved in that reaction. And then enthalpy is the heat that is involved in a chemical reaction, either produced by the chemical reaction, those are reactions that get warm, or it is absorbed by a chemical reaction, those are the reactions that feel cold to the touch. So let's talk about chemical quantities. Let's talk about something simple and look at these different formulas for different compounds or different substances. And ask the question, how many oxygens are in each of these formulas, formula units or molecules or compounds. So look at the first one, CaCO3. This is calcium carbonate. And you can see from the formula there are exactly 3 oxygens in this formula. There's 1 calcium, 1 carbon, and 3 oxygens. We don't write the number 1 if there's only one of that atom. The second molecule is aluminum sulfate. We can see that there are 2 aluminums, and there are 3 whole sulfate groups. Each sulfate group is an SO4, so we have a total of 3 of everything in the parentheses. Therefore, we have 3 sulfurs, and we have 3 times 4, or 12 oxygens in this formula unit. The next one is sodium phosphate dodecahydrate. This is a substance where you have one formula unit, sodium phosphate, that is tightly bound in its crystal structure to 12 waters for every one of these Na3PO4s formulas. So there are a lot of waters in the crystal. You don't see it as liquid water. They're actually part of the crystal. And in this case, we count this as all one substance. So in this particular formula, we would say that the sodium phosphate contributes 4 oxygen atoms, and the 12 whole waters, so the 12 refers to all of the H2O. So we have 12 times an H2O. That means there are 24 atoms of hydrogen, 12 times 2, and there are 12 times 1, or 12 atoms of oxygen from the waters. So we have a total of 4 oxygens plus 12 oxygens for a total of 16 oxygens in this particular formula. The last one in this group is turquoise, and this is the actual mineral turquoise, and it has embedded in it 4 molecules of water. It is a tetrahydrate, hydrate meaning it has waters tightly associated with it in this crystal. So we have, you'll notice the phosphate portion, the PO4, we have 4 phosphates for a total of 16 oxygens. We have 8 hydroxides, that's the OH group, those are 2 different polyatomic ions. 8 hydroxides, so that's another 8 oxygens and 8 hydrogens, but we're only counting the oxygens right now. And then we have 4 whole waters, so that's an additional 4 oxygens. So we have 16 plus 8 is 24, plus an additional 4 makes 28. So there are totals right here, and you can practice those on your own. So this is a question that says how many ions in each of the following. So remember, ionic compounds, most of them will dissolve in water. They're soluble in water. And what that means is that when they are put in water, they will break apart into their component cations and anions. So sodium chloride will break apart into its Na plus and its Cl minus. So a total of 2 ions for every single formula unit NaCl. Potassium bromide will form a total of 3 ions. 1 calcium ion, Ca plus 2, and 2 separate bromide ions, Br minus. So we have a total of 3, even though there are only 2 kinds of ions. Chromium 6 nitrate will break apart into the chromium 6 ion and 6 individual nitrate ions for a total of 7 ions. And the last one is rhenium 7 dichromate. So the dichromate is a polyatomic ion just like nitrate. And we have 7 of them in this particular formula and 2 rhenium ions. The 2 rhenium ions are both plus 7. It's not written here, but they're both plus 7. And 7 dichromate ions for a total of 9 ions. So that's how we count the individual pieces of a molecule or a formula unit. In the first case, we counted atoms of oxygen. In the second case, we counted all the different kinds of ions. So let's look at how we measure things in the lab. If we want to measure mass, we typically measure it in grams, and we use one of these electronic mass balances. If we want to measure volume, it's typically in liters, or if we're measuring smaller volumes, milliliters, or even smaller volumes, microliters, if you're working in a more high-tech lab. And we would use graduated cylinders to measure it typically in milliliters. So that's volume and mass. And these are very easy to measure in the lab. But what we really want to know is how many molecules we're dealing with, or how many formula units, or how many atoms, or how many ions. And when we count those, we have a lot of those, so we don't count them by ones or tens or hundreds. We count them with that large number I showed you in the beginning of this talk called a mole. And so a mole is not this kind of mole, and it's certainly not this kind of mole, and it's definitely not this kind of mole. A mole is a really large number. It's a really large number that happens to have a name. And we use this really large number because it's convenient for counting a huge number of incredibly tiny particles like atoms or molecules or ions or formula units. We have other numbers that have names. 12, we call a dozen. 144, which is a dozen, we call a gross. 1,000,000, we have a word for that, a million. So this number, 6.02214,076 times 10 to the 23, we call a mole. We also call this Avogadro's constant, named after famous Italian scientist Amadeus Avogadro, in his honor. He didn't discover the number, it was named in his honor. But we don't usually use the whole number with all the significant digits. We only use the first 4 sig figs for this. So the number you're going to use over and over again is 6.022 times 10 to the 23rd power. And this was originally determined, I know this is a very odd number, it's not a round number at all, it's a strange looking number. And the reason this number was picked is it was the amount of particles found in exactly 12 grams, or as close as anybody could measure, as 12 grams, as close as they could, of carbon-12, only pure carbon-12 isotope. So they had to measure as close to 12 grams as possible using an incredibly powerful scale. And they had to use as pure a sample of carbon-12 isotope as possible with no other naturally occurring isotopes. And when they did that, they were able to count how many particles, and they counted this gigantic number. And every year, somebody would count it a little more accurately, but then last year, 2019, they decided, okay, let's just set it at this value. So this is the value that it is, and it's now an exact number. So it doesn't exactly match 12 grams anymore. It actually matches a number very close to 12, about 11.999999958 or something like that grams of carbon, but close enough to 12 grams. So Avogadro's constant, or a mole, is a mole, this large number, really refers to the number of particles in a mole. So in other words, it's how many particles that are equal to 1 mole. 1 mole is this many particles, and particles can mean anything. Particles can mean atoms, or molecules, or formula units, or ions, whatever kind of particle you want. And because this number has a unit that is clearly a unit that is based on a numerator and a denominator, in other words, you have particles divided by moles in the unit, this allows you to convert the number of particles that somebody might have to the number of moles that they have, or vice versa. Anytime you have a number, a value that somebody's given you that has a unit that's something per something, that value can be used as a conversion factor between those two units. So if I gave you the number of moles, you could calculate the number of particles. If I gave you the number of particles, you can calculate the number of moles. And particles, if we're talking about elements, can mean atoms or occasionally molecules with some elements. For covalent compounds, it will mean molecules. For ionic compounds, it means formulas. For ions, it means ions. So particles, anytime you see a problem that says how many atoms, how many molecules, how many formula units, you're going to use Avogadro's constant and just replace the word particles with the type of particle you're interested in: atoms, molecules, formula units, ions. It doesn't matter because it will work for anything. It doesn't matter what we're counting. It could be any of these particles. It could be marbles. It could be cars. It could be people if there were that many people, but there aren't. So any count of this number is a mole of that particular object. So it's always, for every single substance, it's the same exact conversion factor. 6.022 times 10 to the 23 of that thing per 1 mole of that thing. In fact, they've even done it for light, and a mole of photons actually has a special name. It's called an Einstein of photons. So let's look at a couple problems that involve Avogadro's number. First one says, how many molecules, okay, that's a type of particle, of CO2, carbon dioxide, are in 4.56 moles of CO2? All right, so you're given a number of moles, and you know that Avogadro's number has the unit moles and particles in it. In this case, our particles are molecules. So we want to build a conversion factor. We start with the value we have. The thing we have in this problem is 4.56 moles of CO2. So that's what we start with. Then we build a conversion factor. And how do we build a conversion factor? Well, here's our conversion factor. You start by making a parentheses, then putting a line in there to divide the top and the bottom. And you see that we have the unit moles, and we want to turn it into the unit molecules. So if we want to get rid of moles, we must put moles on the bottom. Pardon me for this sloppy looking letter. And we put the molecules on the top. And I'll probably run out of space here. Put molecules right there. And now, using Avogadro's number, you know 1 mole equals Avogadro's number worth of molecules. And we abbreviate Avogadro's numbers in some sub-AV for Avogadro. You would just write in this value right here instead. And then you multiply it out, and you get that there's a very, very large number of molecules for this small number of moles, which makes sense because 1 mole is already a huge number of molecules. 4.56 moles will be even more. So we'll look at the rest of these problems. How many moles of water is 5.86 times 10 to the 21 molecules? Well, you always start with the thing you have, 5.86 times 10 to the 21 molecules of water, and then you're going to use Avogadro's constant, but you will this time flip it because you want molecules on the bottom so that it will cancel that old unit, and it will create the unit you want, moles, in the end. And you multiply it together, and you realize this gigantic number of molecules of water corresponds to actually a very small number of moles, 0.00975, and that makes sense because you can see right here, this number is about 1/100th of a mole, and in fact, that's what we get. About 1/100th, a 100th would be 0.01, and in fact, that's very close to 0.01 moles. It's a little bit less. And so our answer makes sense. Let's look at the next problem. How many atoms of carbon are in 0.000000134 moles of glucose? And the formula for glucose is C6H12O6, which means each molecule of glucose has 6 carbons in it. Well, we're asked how many atoms of carbon, and we're given how many moles of glucose. Well, we know that we can take moles of glucose and we can use Avogadro's number. So I'm mapping out a little pathway here. We can use Avogadro's number to figure out how many molecules of glucose we have, and GLC is the appropriate abbreviation for glucose. And then once we know how many molecules of glucose we have, well, we know that every one of those has 6 atoms of carbon, so we just multiply it by 6 to get the number of molecules of carbon. And that's our pathway. So let's do that. We'll do it one step at a time. First, we'll figure out how many moles of glucose, and then we'll turn that into, how many molecules of glucose, and then we'll turn that into atoms. I said molecules. That should be atoms, my bad. Atoms of carbon. So we will erase this note here and go through it. And so the first part of this problem starts with the thing you have, and you know that using Avogadro's number, written with molecules on the top and moles on the bottom of glucose, will give you molecules of glucose. And now that we have molecules of glucose, we know there are 6 atoms of carbon per one molecule of glucose, and that can be a conversion factor. And that will cancel molecules of glucose with molecules, and all we'll be left with is atoms of carbon, and that is our new unit. And you can see we started with a very, very small number of moles, but we still ended up with a very large number of atoms of carbon because we had a very large number of atoms of glucose, which makes sense because there are many, many molecules of glucose in a single mole. So even if you have much less than 1 mole, you're still going to have a lot of molecules and therefore a lot of atoms in the process. And this last problem starts with moles. It starts with formula units, and it asks for moles. How many moles is 7.78 times 10 to the 22 formula units of magnesium chloride? So we start with the thing we have, formula units, and we know Avogadro's number says 1 mole of any substance will be this number of formula units, in this case, of magnesium chloride, and we multiply it out. In this case, we're actually doing division, and you get this many moles. And that makes sense because if you look at the original number, it's a little bit less than a mole, than the mole number, than Avogadro's number. It's about 1/10 of Avogadro's number, maybe a little more than 1/10. And sure enough, we got a little more than 1/10 moles of magnesium chloride, so everything makes total sense.